95% of the universe is completely invisible to us. Every telescope ever built, every satellite ever launched, every photograph ever taken of the cosmos, all of it has captured just 5% of what actually exists out there. The rest? Hidden, silent, beyond the reach of any instrument we've ever made. And here's what makes that truly unsettling. The darkness isn't empty. We live in a universe that appears lit by billions of stars, threaded by glowing nebulae, and mapped by light stretching back 13.8 billion years. But that light is a thin veneer, a sliver of reality draped over something vast and unknown that we are only beginning to describe, let alone understand. The universe, as we know it, is the minority. The darkness is the majority. And what lives inside that darkness changes everything we thought we knew about where we are and what we're made of. Let's start with the most abundant invisible thing in the cosmos. It makes up 27% of everything that exists. You're surrounded by it right now. It's passing through your body as you watch this, and we have absolutely no idea what it is. Dark matter. The word matter is almost misleading because this substance does not behave like anything matter is supposed to do. It doesn't absorb light. It doesn't reflect light. It doesn't emit it. You could point every X-ray telescope, every radio dish, every optical observatory on Earth directly at a cloud of dark matter and see absolutely nothing. It is, by every definition of the word, invisible. So how do we know it's real? Because it's impossibly heavy. And gravity, unlike light, does not care about being seen. When astronomers in the 1970s began carefully measuring the rotational speed of galaxies, something was wrong. Badly wrong. A galaxy is held together by gravity, the gravity of all the stars, gas, and dust inside it. The outermost stars should orbit slowly, like the outer planets in our solar system, because they're far from the gravitational center. But they don't. They spin at the same speed as the stars near the core, sometimes faster. The math doesn't work, unless there's something else. Something massive, spread through and around the galaxy in a vast invisible halo, providing the extra gravitational weight to keep it from flying apart. That something is dark matter. Then came the Bullet Cluster, 3.8 billion light-years away. Two colossal galaxy clusters that collided billions of years ago at millions of miles per hour. When clusters collide, the normal hot gas, the visible stuff, crashes together, slows down, and piles up in the middle. But the dark matter doesn't stop. It has no charge, no electromagnetic interaction. It passes through itself like two ghosts walking through a wall. Scientists mapped the total mass of both clusters using gravitational lensing, watching how background galaxies were distorted, and the mass wasn't where the glowing gas was. It was out ahead, separated exactly where a cloud of collisionless invisible matter would be if it had sailed right through the collision undisturbed. That image is still the most direct evidence we have that dark matter is real. But what is it made of? That question has haunted physics for 50 years. The leading candidates are particles called WIMPs, weakly interacting massive particles, heavy, slow-moving, and touching our world only through gravity. Then there are axions, far lighter, theorized to solve an entirely different problem in particle physics, and now considered equally plausible. Sterile neutrinos, primordial black holes, none of them confirmed. Not a single dark matter particle has ever been directly detected, despite miles-deep detectors built in old mines, supercooled to near absolute zero, waiting for a single interaction that has never come. 27% of the universe, and we don't know what it is. Now make that number feel small. Dark energy accounts for 68% of everything. If dark matter is mysterious, dark energy is something else entirely. A force we don't just fail to explain, but barely know how to describe. It was discovered by accident, in 1998, when two independent teams of astronomers were measuring how quickly the universe's expansion was slowing down. They expected it to be slowing. Everything massive should eventually pull back on itself. Gravity is universal. It reaches across all of space. What they found instead earned a Nobel Prize, and shook cosmology to its core. The universe is not slowing down. It is accelerating. Something is pushing space itself outward, faster and faster, and has been for the last 6 billion years. That something is dark energy. The simplest explanation is that space is not empty, that even a perfect vacuum carries a baseline energy, what physicists call the cosmological constant. The energy of nothing. Every cubic inch of empty space contains a tiny, fixed amount of energy, and because space is expanding, new space is being created, and all of it carries that energy. Add it up across the entire observable universe, and you get an outward pressure that overwhelms gravity on the grandest scales. The problem, the theoretical prediction for the energy density of the vacuum is off from the measured value by a factor of 10 to the 120. That is not a rounding error. That is the single largest discrepancy in the history of science, and nobody knows why. What we do know is the consequence. Dark energy is winning. Galaxies beyond a certain distance are already receding from us faster than light. Not because they're moving through space faster than light, that's impossible, but because space itself is expanding, and the distance between us and them is growing at a rate that exceeds light speed. Those galaxies are already gone from our future. Their light will never reach us. The universe is pulling itself apart at the seams, slowly, relentlessly, driven by something we cannot see, cannot touch, and cannot turn off. 68%. And we don't know what it is either. But the darkness of deep space isn't the only darkness. Go back far enough in time and you reach a period when there was no light at all. Not because the universe didn't exist, but because nothing in it had yet ignited. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to bond with protons and form the first hydrogen atoms. Before that moment, space had been a superheated plasma, opaque and blinding. When hydrogen formed, the plasma cleared, and for the first time, the universe became transparent. That is the moment we see when we look at the cosmic microwave background, the moment light was set free. But the universe that became transparent was not a universe filled with stars. It was a universe filled with nothing but cooling hydrogen and helium, slowly thickening in regions where dark matter had already begun to gather. And for the next several 100 million years, there was no starlight, no galaxies, no visible light of any kind, just darkness and silence and gravity, quietly doing its work. This period is called the Cosmic Dark Ages. It lasted somewhere between 200 and 500 million years, 500 million years of absolute universal night. The darkness wasn't a backdrop for something, it was everything. The universe, by any measure, had not yet begun to live. Then, in the densest clumps where gas and dark matter had concentrated, the pressure became extreme enough to ignite nuclear fusion. The first stars switched on. They were nothing like our sun. Some of them were 300 times as massive, 1,000,000 times as luminous, burning so hot and so fast that they exploded as supernovae within a few million years. Their radiation ripped through the surrounding hydrogen, ionizing it, and slowly, over hundreds of millions more years, the fog of the Dark Ages lifted as the universe was re-ionized. We have never directly observed a single star from the cosmic Dark Ages. They are too old, too faint, too far. The James Webb Space Telescope is getting close. It has imaged galaxies from just a few 100 million years after the Big Bang. But the very first stars remain invisible, lost somewhere in the earliest chapters of a story we are still learning to read. Now turn your attention to something closer, something that should be ordinary, the space between stars. When you look up at a night sky and see blackness between the stars, you might assume that blackness is emptiness. It isn't. The region between stars within our galaxy, called the interstellar medium, is filled with gas, dust, magnetic fields, and cosmic rays. Roughly 99% of that interstellar matter is gas. Hydrogen and helium in various states of ionization, temperature, and density. The remaining 1% is dust, tiny particles less than 1 micron across, forged in the dying atmospheres of old stars and blasted outward by stellar winds and supernovae. That dust matters. It blocks our view. Dense molecular clouds, the cold, dark regions where new stars are born, are so thick with interstellar dust that visible light cannot penetrate them at all. The famous pillars of creation, the dark rifts in the Milky Way's band, the black nebulae scattered across the night sky, none of it is empty. All of it is structure. The darkness between stars is a medium, not a void. But even that interstellar medium is thinly spread compared to the spaces between galaxies and the spaces between groups of galaxies. Step back far enough, and the universe organizes itself into a structure called the cosmic web. Immense filaments of galaxies and dark matter stretching across hundreds of millions of light years, separated by supervoids that span 1 billion light years or more. Those voids make up roughly 80% of the observable universe's volume. Vast, near-empty regions where almost nothing exists. No galaxies, no gas worth measuring. Just the thin residue of dark matter and the slow crawl of dark energy pulling everything apart. And inside one of those supervoids, 1.8 billion light-years wide, containing 30% less matter than its surroundings, physicists believe they have found the source of one of the strangest anomalies in modern cosmology. The cosmic microwave background is the oldest light we can detect. It's the afterglow of the Big Bang itself, radiation that has been traveling since the universe was 380,000 years old. When we map it across the entire sky, it should look almost perfectly uniform, with tiny temperature variations of just fractions of a degree, and mostly it does. But in the southern sky, in the direction of the constellation Eridanus, there is a cold region, colder than it should be, a patch roughly 500 million light-years across, running about 0.0007 degrees colder than the average, and the probability of that occurring by chance, in our standard model of the universe, is estimated at roughly 1 in 2,000. Scientists call it the cold spot, and nobody fully agrees on what it is. The most widely accepted explanation involves the Eridanus supervoid, that massive hole in the large-scale structure of the universe. CMB photons traveling through a supervoid lose energy through what's called the integrated Sachs-Wolf effect, arriving slightly cooler than they should. The supervoid is real, it's been confirmed by multiple surveys. But the math doesn't fully work. The supervoid alone doesn't produce quite enough cooling to explain the entire anomaly. Something may be adding to it. Some researchers have proposed that the cold spot is a scar, an imprint left by a collision between our universe and another. Not science fiction. A mathematical prediction of inflation theory, the leading framework for what happened in the first fractions of a second after the Big Bang. If our universe began as one bubble in a sea of bubbles, and if another bubble universe grazed ours in the inflationary period, it would leave a thermal imprint on the CMB. The cold spot's size, shape, and temperature profile are not inconsistent with that model. It has not been proven, but it has not been ruled out. And then there is the dipole repeller. Our galaxy is not sitting still. The Milky Way is hurtling through space at approximately 1.3 million miles per hour, pulled toward a massive concentration of galaxies called the Shapley supercluster. Astronomers assumed the Shapley was doing all the pulling. Then, in 2017, researchers mapped the flow of thousands of galaxies and discovered something unexpected. We are not only being pulled, we are also being pushed from behind, from a direction in the sky directly opposite to Shapley, a vast, galaxy-sparse region that exerts its influence not through attraction, but through absence. It's called the dipole repeller, located roughly 720 million light-years away. A colossal void in the cosmic web, so depleted of matter that the gravitational imbalance between it and denser regions around us creates a net push. We are fleeing its emptiness as much as we are chasing Shapley's mass. The universe moves not just toward density, but away from void. The darkness itself is a force. Now step to the edge of everything we can observe. 46.5 billion light-years in every direction. That is the radius of our observable universe. A sphere, 93 billion light-years across. Every galaxy, every quasar, every photon we have ever detected comes from inside that boundary. But the universe does not stop at that edge. It continues. How far? We don't know. Possibly infinitely. According to the theory of cosmic inflation, which describes the exponential expansion of space in the first fraction of a second after the Big Bang, the true size of the universe could be at least 10 to the power of 23 times larger than what we can see. Some models suggest it may be infinite. The boundary of the observable universe isn't a wall, it's a horizon. Beyond it, galaxies exist. Stars burn. Perhaps structures every bit as complex as our own local supercluster extend through space in patterns we will never map. We cannot see them not because they aren't there, but because their light has not had time to reach us. And in many cases, because dark energy is accelerating space faster than that light will ever travel. Those galaxies are not just currently invisible, they are permanently invisible. They have already crossed our cosmic event horizon. Whatever signal they emit today will never arrive. We are enclosed in a bubble of information. Everything outside is, by definition, unknowable to us. Consider what that means. The darkness beyond our observable universe could contain exact copies of Earth. Not metaphorically, but mathematically. In an infinite universe with finite combinations of matter, quantum mechanics predicts that every configuration of matter that can exist will exist. Somewhere, infinite times over. Somewhere in that darkness, this moment may already have happened. You may already be watching this video, hearing this exact sentence for the second time. Or none of that is true, because we cannot see it. We cannot test it. The darkness in the end may be the only mystery that science can never fully solve. Not because we aren't smart enough, but because the universe built a wall of light speed and time and made the answers physically unreachable. 5%. That is the universe we live in. A thin layer of visible, measurable, nameable matter floating in an ocean of dark matter, dark energy, and cosmic voids so vast they bend the path of entire galaxy clusters. The darkness isn't nothing. The darkness is most of everything, and we are only just beginning to ask the right questions. So here's what I want to know from you. Which part of this unsettles you the most? The fact that we don't know what 95% of the universe is made of, or the fact that there may be parts of it we can never reach, no matter how advanced we become? Drop your answer in the comments. I read every single one. If this video made you look at the night sky differently, hit the like button, and share it with someone who still thinks space is mostly empty. And if you want to keep going down this rabbit hole, make sure you're subscribed, because the next video covers something equally strange. What happens at the absolute end of the universe, when the last stars burn out and only darkness remains?